Sport and Health Sciences at the University of Brighton. And I would like to dive in straight into the presentation by introducing some initial concept of regional masking analysis for those of you who are not familiar. So as you can see from the video, regional masking analysis consists in dividing the plantar surface of the foot of these pressure images in several regions of interest that correspond to anatomical parts of the foot. And you can use as many regions as you want, many regions as you need. And this is the conventional approach for analysis of plantar pressure data, as I said, and it's widely adopted for infants, children, and adults. And it's quite easy to use. There is no need to understand programming languages, which makes it quite intuitive. And you can also, as you see from the video, draw manually regions of interest around anatomical areas of the foot that you want to analyze. And also you can modify these regions by translating into other parts of the foot. And you can also, you'll see that in a minute, yeah. And you can also modify the regions by making them bigger or smaller, depending what you need. And basically this approach is highly accessible to clinician and researcher. However, it comes with certain limitation. And first of all, discrete data treatment, because we basically just analyze each region separately without considering the continuum of the foot. And we make also underlying assumption of regional independence because, as I said before, we consider regions separately. Although we know that during a stance phase, all the anatomical structure of the foot collaborate with each other to enhance forward progression. And these two limitations relates both to infants and adults pressure data. And I added another limitation with this approach that relates mainly to infants pressure data. And it's the lack of clear anatomical definition on the plantar surface and hypotheses relating to the region typically analyzed in the plantar pressure field, which means that basically if you have a look at these images, you see that the adult's feet are quite well defined and you can identify the heel, the forefoot, the hallux, while, for example, if you look at the infant foot, it's more or less like a blob, that it's really unshaped, and using a software that has been implemented to analyze adults' feet, and it's based on adults' feet algorithms, it's a limitation in itself when we analyze infants' feet, because the infant foot is developing smaller and it's pretty much very different. So as an alternative, we could use pedobarographic statistical parametric mapping that we call from now on PSPM. And PSPM has been introduced first in 1995 for human brain mapping, specifically cerebral flow analysis, and is being applied to the plantar pressure field in 2008. And it comes with certain advantages, such as it conducts statistical inference at pixel level, so we have a continuous statistical analysis as opposed to discrete. And in this way, PSPM treats plantar pressure data in its meaningful two-dimensional field, and changes in pressure, so for example, increasing or decreasing pressure, are visible in the spatial domain of the foot, so in the anatomical correspondence of where these changes happen. And PSPM has been used already quite a few times in adults. I reported some example here. It's been used once for children, pressure analysis between 4 and 7 years. And it was never been used for infancy. And there are several reasons as to why this might happen. One of the first one that comes to mind is that collecting biomechanical data in infancy, it's quite a challenge, and also the data itself, it's difficult to analyze because it's embedded with variability, intra and inter-individual variability. So it's not easy to collect. If for those of you who collected biomechanical data in infancy, you all know that it's really tricky and challenging. So the aim of this work was to detail the implementation of the PSPM data processing framework. And by adopting this framework, we wanted to compare also plantar pressure in new and confident walking infants. And for the purpose of this work, we recruited 12 participants, 6 females and 6 males. We obtained ethics and informed consent by the parents. And we collected the data by milestones of development. So we asked parents to come to our lab when infants were able to take the first 3 to 5 independent steps. And then we asked them to come back when they were able to walk 10 to 15 steps independently and confidently. And we used 72 pressure images for both milestone and for left and right feet together. And the space where we collected the data was a nursery-style environment where we placed an image Excel platform in the middle with a sensor resolution of 4 sensors per centimeter square. And we let infants walk in any direction on the platform without constraining them into straight line walking, because we wanted to capture their everyday walking pattern and behavior. So this, however, led us to capture plantar pressure data that was highly variable in shape and spatial orientation, as you can see, and also was characterized by high intra and inter-individual variation of pressure magnitude and distribution. And therefore, we started our processing framework by transforming the ASCII extracted files of these pressure images in two-dimensional matrices, and we embedded these matrices in a grid of 36 times 25 pixels. Then we transformed the images in point cloud, and we took out pressure out of each pixel or point, and we vectorized pressure data for each pressure image of each infant. And then we performed within subject data registration using a rigid IC iterated closest point algorithm that enabled to translate and rotate the point cloud onto the within subject template. However, as you see from the example I reported in the image that I reported, the initial data registration was, the quality was quite poor, and this, we realized that this was mainly due to the ICP algorithm being quite susceptible to local minima, and its performance relying on the initial pose estimation of the point cloud with respect to the template. So we realized that we needed to perform another important passage within this processing framework, which was the rotation of each pressure images with respect to a common rotational system. So we performed a principal component analysis by binarizing the pressure images first. We found the centroid of each image, and then we calculated the covariance matrix of each image to understand whether the footprints were pointing towards left or right. Then we calculated eigenvectors of the matrices and reported them as a principal axis of the matrices. And we calculated theta as the angle forming between the longitudinal axis of the foot and the parallel to the y-axis of the reference system of the pressure images. And we applied this theta to the rotational matrix, having this general form, which allowed us to rotate the pressure images in an anti-clockwise manner to vertical. After this, we retransformed each pressure image to a point cloud, and we reperformed within subject registration with the rigid ICP algorithm. And you can we saw straight away that the results were already more promising than the earlier algorithm because we already detected like an improvement in the registration quality. And then we perform within subject morphological averaging to reduce the differences in the shape of the feet within the same infant. And we calculated also within subject pressure vector that we used later on for the analysis. And as final step, we register the footprints between subject using a non-rigid coherent point drift algorithm that enabled us to rotate, translate, and scale the point cloud of all the infant to a common template that was chosen as the template which length and width was closer to the mean length and width of all the feet of all the participants. Statistical analysis that we performed was divided in two phases. So we first wanted to know how our approach performed on this data set. So we calculated root mean square error as a measure of the within and between subject registration quality. So for the calculation, RMSE was calculated as the Euclidean distance for each coordinate points between the surface of the within subject template and the point cloud of each infant. And also in the context of between subject registration, RMSE was calculated between the surface of the common template among all the subjects and the mean point cloud for each infant and milestone. And for the main plantar pressure inference, we performed a non-parametric SPM1D tilde per t-test between pressure data of infants at the two different milestones. And then we also perform non-parametric SPM1D linear regression between body weight and pressure. And you can find these statistical packages at this link if you're interested. Our results allowed us to make some methodological consideration related to our approach. So as you can see, for both within subject and between subject registration, the root mean square error was quite low, so below 0.4 millimeters. And the standard deviation of RMSE were also pretty low, which basically told us that the ICP, both ICP and the CPD algorithms performed consistently across our data set. And visually, you can see that the ICP, the overlap of points for within subject registration, it's more precise than the overlaps of points for the between subject registration. And this might be due to the fact that although highly variable, it's reasonable to say that within the same infant, there is a more, feet are more similar, whilst between infants, obviously there are more and more differences, especially within this data set. Regarding functional consideration, so our main statistical inference detected a significant increase in pressure in the central left forefoot. And I added here a little legend for you, so you can also interpret the results. But apart from the significant increase in pressure, we can mainly detect non-significant increase in pressure across on the plantar surface of both feet. And specifically in the right foot, you can see that the central, lateral to central forefoot is characterized by a large area of a non-significant increase in pressure. And in the paper, we try to give an explanation as to why we have significant differences just in one foot and not in the other one. We normally, in adults or older children pressure study, we see that differences are similar between feet, and in this case are not. And we basically found this paper describing the presence of interlimb asymmetry in early walking, where one limb was used to for propulsion and the other limb was used for balancing purposes. So we cannot say that these results apply to our data set because of the differences in the sample, but it's definitely something that it's worth to consider in future studies and making perhaps some consideration related to interlimb asymmetry and plantar pressure data. But apart from this, we try to give also explanation as to why plantar pressure significantly increased in the central forefoot. And we started by considering anatomical changes. So we have this paper, the only one paper that used this approach in children, that found that pressure increased significantly in the central forefoot between 4 and 7 years. And the authors in this case argued about development of the anatomy of the foot, specifically changes in posture of the metatarsal bones and increasing joint stiffness. However, in our case, the observational gap was to just 2.3 months. So it's really unlikely that anatomical changes would happen at a rate that would influence plantar pressure. So we exclude this as a possible explanation. We also performed linear regression analysis between body weight and pressure to check whether body weight could have something to deal with increasing pressure, but the SPM analysis failed to demonstrate any relationship between these two factors, thereby excluding body weight in this case also as a possible explanation. And we found an early paper looking at early walking as we did, and the authors found that basically infant running exhibited more pressure in the central forefoot respect to the infant walking. And this makes sense in our case because if you think Okay, sorry. If you think about infants that are just starting to walk, they're a bit of they're clumsy. They are not really confident, so they mainly progress like really slow. They try to balance. As soon as they start to walk more confident, they want to explore more. They want to interact with parents or toys. So an increasing walking speed seems a very reasonable factor affecting pressure in this case. And these results were never reported before, so they're pretty unique. And the reason why nobody has ever found these patterns here is probably because the methodological approach used so far. So as I said already at the beginning, regional masking analysis is the conventional approach for plantar pressure studies. And if you, for example, take a look at this 5-region mask, which is one of the most used masks in the plantar pressure field, you see that they consider forefoot as a whole. So when you deal with peak pressure images, you are basically just detecting the sensors where the pressure is the highest. And if you don't know where these sensors are, so if you don't know where these pixels are, you can't really tell in this case where are the differences. So the differences between new and confident walkers might have been detected in the central forefoot or in the medial lateral forefoot. But if you consider a region as a whole, you don't have this detailed visualization of the differences. And you might also think like, okay, well, let's divide the foot in more regions so we are more precise. Well, in our case, we detected differences in the central forefoot. And if you divide the foot, let's say in mediolateral components, you might have gotten these differences on the midline, or perhaps like shifted 1 inch towards the lateral forefoot or 1 inch towards the medial forefoot. And this would have changed completely our interpretation of the results. So in conclusion, we demonstrated a robust applicability of the Pedobarographic statistical parametric mapping data processing framework on infancy. And we were able to detect also novel plantar pressure changes, which highlighted rapid foot function development from the onset of walking to confident walking. And as I said before, one of the possible future direction coming from this work would be to explore the presence of limb asymmetry in walking infants, which has been scarcely reported. And also an interesting point would be to combine interlimb asymmetry studies with pressure to see whether there is really a presence of different function within the limb that affects pressure, plantar pressure data. And we are currently working to apply this processing framework to a larger data set that would explore in-depth patterns of function and its changes with increasing walking experience. Would like to thank you for the attention, and if you want to read the paper and you didn't get the chance to read the paper, you can email at my email address and I'll be happy to send it to you. And yeah, thank you very much.
Thanks to you, Eleonora, for the presentation. It was really nice, very clear, and very clear message, especially about the relevance of your study. And so with this, I would like to open the session for any questions from the audience. So if you have any questions, feel free to just raise your hand, or since we're actually quite a few people at the moment, you can just unmute yourself and ask the question directly. If not, I can at least maybe start with some icebreakers. So yeah, actually, I was really curious, like about when I was reading your paper, and especially I really like the way you try to understand which are the potential causes or the potential factors that led to this difference. So I was very impressed when I was reading, okay, you're actually checking for the correlation with the body weight, and especially on how well you differentiated between functional interpretation and potential morphological differentiations. So yeah, congratulations for that. I was really reading the paper. I think, okay, I would like to do this, and then it was coming. So that's always nice when you like try to.
Thank you.
And then yeah, and and I agree with you. Like I think like okay, the 2 months differences between like on average between the two time points are probably too short to identify differences in morphology. And yeah, most likely the reason is difference in functionality and potentially push-off. Actually, I think push-off is quite important when you're trying to like it's something that you really have to learn when you're learning how to walk, basically. And this is where most of the pressure come off. Could also be somehow maybe proven with a EMG of the triceps surae. I mean, I guess in many ways, yeah.
One of the big challenge that we are trying to overcome is to combine the different biomechanical analysis, and the biomechanical data collection. So we are trying to combine kinematics with pressure, EMG with pressure. Problem is that with infant data, there is always a challenge because basically their footprints are all over the place. The motion segments are all over the place. There is so many challenges. So we are working on it, but it's really, really difficult.
So I mean, I haven't really worked with infants, but I participated in a few measurements with like with children or adolescents, and even there sometimes it's difficult. I mean, their attention span or their motivation to follow instruction is very limited. So I think this is actually where the potential of your study comes in, because in that sense, you're less dependent on constraining the setup or putting on markers and really have the patient walking a direct way. If you can really prove that the pressure footprints that you get are directly linked to functionality, you can evaluate really functionality in a free environment without really constraining the motion of a child. So I think in that this is really the potential when you start to link different factors that until now were not really associated with function, and now you're actually showing that there is a direct correspondence with it. So I'm really curious to see where this is going.
Well, I hope I won't let you down. There is something coming up, so well, let's see if it's up to the expectation or not.
But then maybe also, can you comment on what's the next step? So you're planning to expand the cohort or do at multiple time points?
So basically, this was first. It was part of part of my PhD, and we tried to implement novel methodology to analyze plantar pressure data. And this sample that we had is the first sample that we collected before the pandemic started. So before we had to shut our lab. So we came up with this sample, and we basically said, why not to do a preliminary test on this methodology, on this sample. And so this is just the first part of the PhD, and then all the other experimental chapter comes as a result of this methodological chapter that I have, where I apply all of these novel methodologies to a larger sample. So at the end, I managed to get 40 infants in the lab instead of just 12. So the same analysis is being almost reproduced on 40 infants, and with other bits here and there to try and see if, as you said before, we can infer something about function with pressure, with this pressure data, and what this pressure data basically tell us about how the infants use their feet as they start as they learn how to walk, basically.
There is a question from Bryce. Like, feel free to ask.
Yeah, cool. Thank you, Enrico, and thank you, Eleanor, for your presentation. Super clear, and I really like the PCA to reorientate the foot, because we are working with plantar pressure data. It's a little bit different, but as soon as the foot goes a little bit sideways, and we're working with adults, which in theory are a bit easier to control, but I think the use of the PCA to reorientate the foot is really, really cool. I would say a bunch, but a couple of questions. Maybe a little bit about the methodology and just some clarifications and maybe suggestions. But I guess just starting from going in order from your presentation, you kind of started off with when you were registering the point clouds. I mean, you're saying like you weren't really getting a really good estimation of the pose, right? which kind of makes sense because I think you were using, and correct me if I'm wrong, but a rigid ICP registration, right?
Yeah.
So in that way, it kind of, well, in its name, it's an iterative closest point, right? So the calculation is between a specific node and its closest point. But because you basically, let's say, reformat all the masks to be the same size, could you not use like a registration that's actually like a node correspondence? So because you have the same exact number of nodes or points, and in theory, the indexing of those would be exactly the same. If you like calculate the error in like a node correspondence rather than a closest point,
so is this approach? Sorry, is this approach that you're saying working on exact correspond like the same amount of points?
Yeah.
So basically, each image needed to have the same amount of pixels, right?
Yeah.
Yeah, I thought about that, but we would have gotten that opportunity if we had used to collect the data pressure insoles, for example, because with the insoles you have the possibility to draw the insole around the foot, like specifically, so you have those sensors that will be loaded and just those sensors. But the problem with pressure platforms is that infant might could load, for example, 12 sensors, and the other infant might load 25.
Yeah, but did you, and maybe I missed it, or misinterpreted, but didn't you say you reformatted the image to be 36 by 25 or something? So
yeah, that was the matrix, but considering also let's say the space around it. So we padded the images in order to make them having the same reference system for consistency, but within that matrix the loaded sensors were very different. Like the number of loaded sensors was different for each image. So we needed something that could be used on a different number of loaded pixels every time, although the matrix was formatted in the same way for every infant.
Okay, yeah, okay, that's fine. That's good clarification because I think I maybe misinterpreted.
Yeah, because I think I wasn't being very clear because you just saw that the image basically cut around there was at a certain point the reference system, and basically the white background were all zero values, and the loaded pixels were values from 10 to whatever. But yeah, they had zero values in the matrix that didn't correspond to actual pressure values.
Okay, that makes sense, and that's the beauty of a journal club. You can ask these clarifications, right?
Yeah, it was a really nice question, actually. Thank you.
Maybe if no one else has any questions, I can jump in with another one. So of course you kind of presented like the comparison where you kind of have like the full footprint, right? But of course you have like when they're walking, you have like the contact and toe off. Did you look at a specific time point? Did you look at an average? How did you that one point?
So these are averaged pressure images. So they are the combination of all the single frames that compose, let's say, a whole step happening from 0 to 100, defining the stance. There is an approach that looked at the whole stance in its spatial-temporal domain. I did just look at the spatial domain of the feet, but the reason behind it is because we started off with the pressure images, with the full pressure images, and if we saw that this was a viable approach, then we would shift to frames of pressure like that. So this kind of spatio-temporal dimensionality that you're talking about, and for this there is this approach called STAPP, which is the spatio-temporal analysis of pressure or plantar pressure. That basically does the same. So there is the registration of the frames, There is the averaging, there is the statistical inference is the same, but it does it with respect to also to where and when these changes happen during stance. Mm-hmm. So we started off with the easy thing. Hopefully we will continue with the tougher stuff.
Yeah. No, I think that maybe goes back to something that Enrico was saying with the propulsion, right? Because I mean, if you think that's something that's different, you're probably maybe more likely to see a difference at the end of stance versus the beginning, right? And I mean, if you think of where you saw that difference at the forefoot, maybe if they're shifting their pressure forward, it's to get more propulsion, whereas they previously maybe shifted backwards to get more stability versus actually trying to actively walk and get a bit more speed, or for lack of a better word. Yeah, it's very interesting.
Thank you.
Imar has a question now.
Yes, I have a question. I also thought that the framework was very interesting and very nice. I was very curious about, I can imagine it's hard to get kids to walk, especially infants. And it's difficult to get a large number of steps on the force on the load sensor. I think in the study you used 3 steps per infant. Do you think that has a big influence, and you have to select them? Do you think the selection has a big influence? Because I imagine especially very newly walking infants might take one step that is just toes and then another one that is a lot of heel. But, you know, like, can you speak a bit to the influence of the number of steps and also which pattern or which pressure profile you actually include and which you exclude?
Yeah, absolutely. And this is one of the, I think, one of the interesting parts of this work, because we basically left the infant doing whatever they wanted over the lab, and we started the platform for 60 seconds every time. So they had 60 seconds to step on the platform and then go. And we did this for let's say for a minimum of 3 times and a maximum of 10. So we also ended up with 10 trials for the same infant, because the infant wasn't particularly performing or wasn't happy, was crying, so we needed to start back. But yeah, basically, especially for infants that just started to walk, the selection of the step was really a thing, because out of 10 steps, for example, let's say that 5 were just blobs, like really undetectable footprints. And that's why we needed to collect this much data to allow us to select the best shaped steps, and also like the most complete ones, because obviously it is their specific characteristics. Like obviously if they just start, if they just step the platform with the forefoot or with the portion of the foot, that's typical of them, so it should be captured. But at the same time, it introduced so much variability in the data that you wouldn't be able either to detect differences, or if the differences are present, they're present because of the differences in basically how they make contact with the platform. So yes, we allowed infants to perform as much as they could, obviously, but we wanted to capture as many trials as we can, because we knew that after the first 2 or 3 infants that came to the lab, we realized that we needed a lot of data to be sure that we had data at the end that could be analyzed. And yes, so I'll say that selection of the steps was one of the main factors that allowed us to then perform this analysis.
Okay. You mentioned that you will, or you have already extended the cohort now to 40 infants. Have you also extended the number of steps that you include, or did you decide?
Yeah, it's like 6 or 8. I think it's 6 now. It's 6 steps per infant. So it's 46, almost 500 steps overall that we analyzed. Considering the amount of data that we had, for me, it doesn't seem like this much. But then if we look at other plantar pressure studies, like 500 pressure images as a data sample, it's quite big. Obviously, for example, variability studies, you need this much for each infant. Yeah, I'm quite happy with the final result and the data sample that we managed to reach.
Maybe I can follow up then on a point you mentioned before, when you have a partial contact of the foot. So I think this is particularly interesting for certain specific pathological populations. So if you think of cerebral palsy or idiopathic toe walker, they tend to walk in an entirely different way.
Yeah.
And so this is actually what I was wondering when I was reading your paper. How could you expand this method of the standardization pipeline that you have to entirely different pathological population, which may have an entirely different contours? So whether it's toe walking or even just a foot deformity, if you think of a club foot deformity, can you basically adapt the method to analyze these populations? And if you try to compare this with the controls, would it be like comparing apples and oranges, or can you actually make a meaningful comparison?
So I think basically this data, it's like a normative data. My data is like a normative data set. So it's more or less what pressure image from an infant that started to walk and just is a confident walker should look like. So like, for example, in a clinical setting, you have an infant walking all over the lab, and you put like a platform in the middle of the lab, and you capture these pressure images. You should be able to detect the same patterns that I did. I think this methodology is transferable to other situations, and obviously it really depends on the data. So it's really difficult for me to say I'm totally sure that it's transferable, because I would need to spend some time with this data, from, you know, club population with club feet or cerebral palsy, because obviously everything, it comes in process as it happened for this paper. So we started off with transformation of point cloud, and then we performed within subject registration, and we realized that we needed another step in the processing framework. So yes, I think I'm confident that it should be transferable, but without having some data to analyze or some data to play with, I cannot be really sure. But basically, on a more clinical perspective, if you have like even if you have like a pressure platform in your clinical settings, and you have children with, for example, clubfoot or cerebral palsy, obviously this data is not like some life-changing data. So it's not that we can cure cerebral palsy with this data, but if in the treatment protocol you want to improve also functionality of the foot with this data, you perhaps want to start some treatment protocol that leads your infant with infants with cerebral palsy or whatever other condition to get closer, their function to get closer to this data. So it's sort of like we know how the foot function in early walkers, so let's try and get closer to how the foot should function. So that's the aim. Hope I answered your question.
Yeah, no, I mean, I also don't know if there is like an answer, as you said. Like, we probably have to try until you face all the challenges that come with it. But I think, yeah, it is still promising. So I think it will be very interesting in the future to see this expanded to also different pathological cohorts. And yeah, maybe you can actually use the journal club with the ESB as a platform to start new collaborations with this.
Absolutely, yeah, it would be great. And also, like, this approach is, it started, like, it's been developed quite a few years ago now, but it's really not that much adopted in the pressure field, probably because of these challenges in the processing framework. I mean, lots of what we did was basically processing, and then once we process, all the rest was easy and comes quite nicely. But processing was, I think, 70% of the work. And I guess this is why it's not this much adopted so far. But there's hope. Like people will know this approach, this procedure, and perhaps we'll find application for this in the near future. I really hope so.
There's
We
another
have a
question.
new question from Bryce.
Maybe a follow-up you said, because yeah, I understand you develop something and then you think it's really cool, which I mean, for this it is, for me at least. But then of course you say, yeah, it's not being adopted. And then you kind of already hinted to the fact that it's 70% processing. Out of pure curiosity, if I have, let's say I have the data, how long does it take to like start processing, like to run the PCA, to analyze the foot, to reorientate it, and then do a comparison for, I don't know, another subject, for example?
I think the most challenging part of the processing is understanding how you can extract the data out of, so you have your pixel image, right? And you have probably a software that extracts a format out of this data. In my case, it was an ASCII format. So it really depends on how your software extracts the data. But once you understand how the data is extracted and how you can create, like, for example, in my case, I used MATLAB. So how you can create files that you can use in MATLAB with that. I think if you know what you need to do, it's not that time consuming. You need to have some passages clear, like if you want to use PSPM, you need to register the images, obviously, and you need to use non-parametric inference for assumption of smoothness and dimensionality of the data. But it's really not that difficult, especially the statistical part. Once you have your matrix with all the pressure for each infant that is being processed, the statistical part, it's really, really easy. It's like a couple of lines of code. The processing, it's doable. And well, I'm happy if I can help anything. If you have any idea and you want to use this, I'm happy to contribute, like to help. Ask.
No, thank you. I think that's the problem that probably a lot of us face is that we think it's very intuitive and very easy to use, but I think a lot of applications where we talk about bringing it to clinic, it needs to be press the button, collect, press the button, processed, press the button, here's my difference, which I think is a challenge, but I think it's also something we should take into account. And I think with the PCA and everything, I think you've already done a lot of the kind of groundwork to kind of make that quite possible, right? I really commend you on that. I think that's really cool.
Yep. For the adoption of the framework, I was actually wondering something else. If at the moment you have this one center or two centers actually, right, with a certain force sensor, and you have this normative data set. If somebody else, let's say, wanted to build the same methodology in their lab, but they have a different force sensor, do you think that's easily transferable, and could they easily compare to your data set if they, for example, got the mean pressure profiles for the different groups? Or do you think, for example, different resolution in the pressure sensor could make a big difference and make it very difficult to compare data sets?
So obviously, if you consider like let's say 12 centimeter foot, which is really, really small, and the lower the resolution, the lower the pressure information that you can collect. And also like frequency, for example, I collected at 100 Hertz, so anything below that. So it's a combination of factors, but I would say well, it's really difficult because if you use like a 2 sensor per centimeter square resolution platform, I would say probably you get close to my results, but perhaps not, because obviously you capture less information. So you might miss some spots, or if you do the same as I did, the same amount of data, the same participants on a, as I said, 2 sensor per centimeter square platform, I wouldn't be surprised if you didn't have significant differences, for example.
Yeah.
But this is just because it's an infant foot, and it's quite small. If we consider like an adult foot, probably yes, we have that. It's always the best to collect data at higher resolution, but probably these differences wouldn't be this drastic in a bigger foot. But yeah, with an infant, I say that the resolution is pretty important.
That makes a lot of sense. Given that you have a big data set, maybe that would be a good starting point for the future to check the resolution by maybe just resampling the images, for example, to different resolutions to see how that comparison would suffer or still work with different data.
Yeah, it's actually a really nice idea. Really nice.
Do we have any other questions from the audience, or should we continue with our discussion? Enrico or Bryce, do you have any more questions?
But nothing from me. I think we covered a lot of things, but I think we've had a lot of chances to ask our questions, which I think is nice. But, yeah.
No, I think one of the, I would say probably not very important questions for this, but if you extended basically your time frames, let's say you had the infants coming in again like 5 months from now and 2 years from now, do you think at some point you would run into limitations basically with the non-rigid registration, just because at the moment it's 2 months, so the foot probably hasn't changed much between subjects, but after 2 years that will be very different, so the rigid registration probably will not work anymore. But yeah, in general, do you think there is a limitation with respect to timeline?
Well, yes, obviously, because the foot would be different in size. So I don't think in that case I would consider a rigid registration, because it doesn't allow you to scale the images. So we just had translation and rotation, but perhaps like enough. I would definitely consider something that enable to stretch the images with respect, probably. I wouldn't say the big one, because then there would be just too many differences. But let's say that you have an infant foot, like a 12 months old infant footprint, and then you have a 5-year-old footprint. I would probably consider, if I collected data longitudinally out of in this range for, let's say, every year, I would probably consider like the footprint to register everything onto being like a 2.5 years, like something in the middle. So it doesn't stretch much, and it doesn't change much from both directions. So either from the small to big and big to small.
Makes sense. Are there plans to collect any such data? I think I saw.
Not at the moment. Not at the moment. I'm almost finished with my PhD as well, because I'm at the end of my 3rd year. So I think, well, it will be definitely, like, I would be happy to continue with, collecting other data and continue with, let's say, normative data for all the pediatric age. But I'd be interested also in looking at like pathological population, as Enrico said before, and see if either this approach can be adopted, or other situation and biomechanical analysis can be carried out. So I think, yeah, perhaps I don't exclude anything, but it will be subject to debate in my head.
Sounds very good. Enrico, do you have any more questions?
Oh, maybe that's the last important one. Are you planning to come to Porto for the ESB? Perfect.
Yes, I submitted an abstract. Well, it was January. So yeah, I definitely, if it get accepted, I'll definitely come. I probably come anyway if it doesn't get accepted, because it's a big event. And finally, we get to attend these conferences in person. So yeah, it will definitely be something I want to do. And it's good that I know already someone, because I'll be coming alone.
Perfect. Then we can rediscuss everything after your presentation there.
Well, if I present something, yes.
Sure.
Sounds great. Then thanks a lot for the discussion. If there are no more questions from the audience or any other how to say it, motivation to discuss. I mean, obviously you will seem to want to follow up during the conference, which is great. I'm looking forward to it as well. And if that's all the questions that we had, then thank you a lot for the discussion.
Thank you guys for having me.
Yeah, it was a very nice presentation and a very nice discussion afterwards.
Thank you very much. And well, I just leave now.